There are already 48 participants at the moment. Many others probably are joining as well, but it's time to start. So I would like to open this webinar. Hope you hear me well. I think it should work fine. So good afternoon, everybody, and welcome to this webinar, Recent Advances on Functional Data Analysis. I am Christian Capezza, and I present this as a member of the editorial board of YoungStatS, and I participate to YoungStatS project, whose coordinator is Andrej Zrakar, and he's going to present YoungStatS project in more detail. I'm also a member of the young group of the Italian Statistical Society, and here we're going to see this webinar on functional data analysis with 3 speakers and 1 discussant. I just briefly mentioned their names, but we're going to present them better later. We have Alessia Caponera, Alexander Volkmann, and Fabio Centofanti, with the discussant, Dr. Juhyun Park. So without wasting too much time, please, I let the floor to Andrej to present YoungStatS project, the coordinator. Thank you, Andrej.
Christian, very, very short words. YoungStatS has been presented also on previous webinars. We welcome you all. YoungStatS is a project taking place in the framework of the Young Statisticians Europe initiative, part of YoungStatS Association. It is supported by Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute of Mathematical Statistics. And I will shortly note, before passing the word again to Christian, that we also have a few webinars scheduled for the fall, very interesting webinars in cooperation with Young Researchers Committee of the Bernoulli Society on machine learning, on concentration inequalities in machine learning, on symbolic data, and on algebraic statistics. There is a second part of the project, which is a blog, but rather not talk about this now. I pass the word again to Christian. Thanks for the short possibility to talk.
Okay, thank you, Andrej, for your very nice presentation of the project. And we are happy to have these, all the speakers and the discussant here are from European affiliations, coherently, I would say, with the fact that YoungStats is a project by Young Statisticians Europe, as well. Of course, we could have welcome also people from other countries or regions, or yes, of course. But I would say, let us start with the presentation. We will go with this order: Alessia first, then Alexander, and then Fabio. And then we will have the discussion from Dr. Park. So the first speaker is Alessia Caponera. Sorry for my bad pronunciation. She's from École polytechnique fédérale de Lausanne. And she's going to present her work, Asymptotic for Spherical Functional Autoregressions. So Alessia, the floor is yours. Thanks.
Thanks. So I'm going to share my screen. Could you see it properly?
Yes, Alessia, we can see it very well.
Okay. So thanks, Christian, for the invitation. I'm very glad to be here today to talk about this joint work with Domenico Marinucci from University of Rome, Tor Vergata, entitled Asymptotics for Spherical Functional Autoregressions. The main framework will be functional data analysis on the sphere. So usually when we talk about functional data, we assume to observe a collection of functions usually defined on a one-dimensional domain. So for instance, the interval 0, 1, 1, 2, up to n observations. Here, instead, we are going to assume to observe function on a spherical domain. So we are going to assume to observe surfaces on the whole sphere. And in particular, these observations sometimes can show some kind of dependence, and that can be taught as a temporal dependence. And this is our main point. So spherical observations, spherical maps, defined on the unit sphere S2, which are realizations from spherical processes temporally dependent. Okay, I'm going to here, for instance, we have some real examples. So the surface temperature or the cloud coverage, which can be observed all over the Earth and at different time points. I'm going to focus first on some preliminary on functional data analysis on the sphere, and then I'm going to focus more on this spherical functional autoregressive model, and I will show you an estimation procedure and some asymptotics results and an application, which is an ongoing work if there is time. So, as I told you, here we have a collection in time, in discrete time, of spherical random fields. So a collection both index of random variables, both index in times and with a point on the sphere X. As usual in functional data analysis, our spherical fields is also a random element of the space of square integral function over the sphere in this case, and we are going to assume zero mean for simplicity and finite variance. Moreover, we are going to add these assumptions, which is very important here. So the field will be spatially isotropic and temporally stationary, which means that the law of our field will be invariant under rotation in space and translation in time. And under these assumptions, we have this spectral representation for any point x on the sphere and any time t. So the field time t and point x can be decomposed into this sum over frequency and with respect to these deterministic functions, which are called spherical harmonics and represent a standard basis on L2, S2. These coefficients here, the ALM, are random coefficients defined as the inner product between the spherical harmonics at multiple Lm and the field at time t. So here we have the dependence in t. And if we look at just one sphere, so fixed time, the ALM in frequencies are uncorrelated. So this represents a proper Karunel level expansion in this case. And instead, if we look at the ALM for fixed frequency Lm and as a function of time, here we have a second order stationary process. So the covariance between the ALM at time t and the ALM at time s depends just on the time, the difference between the two time points, so translation in time. Now we are going to focus on our specific model, so the spherical autoregressive model. We consider two isotropic stationary spherical random fields, so T and Z, and we assume Gaussianity. In particular, Z is a Gaussian spherical white noise, so it's a collection of spherical random fields that are IID, so not dependent in time and identically distributed. And this phi is an operator which takes as input a function in L2, S2, and here it is called isotropic kernel operator because it is an integral operator depending on this kernel, which we call it isotropic in the sense that it depends just on this inner product between the 2 points x and y. So intrinsically, it depends on the geodesic distance between the 2 points. And for a spherical autoregressive process over the one, so the simplest case, we have that our field at time t can be decomposed into these two parts. So this part Z, which is the noise, and so an innovation part, and this part which describe the linear dependence between the field at time t-1 and the field at time t. So phi is a linear operator. And here we have the comparison with the standard autoregressive model where we have the linear part So we have scalar parameters which multiplies a random variable. Here we have a linear operator which takes as input a random function. And this is a formal definition for the general case of a Spherical model. So here we have phi1, phi p integral operator associated respectively to their kernels k1, kp. This kernel k will be our object of interest, so we are going to, our goal is to estimate k. And a nice thing to observe is that if we have a spherical random, spherical autoregressive process for the spherical field, here at the level of the coefficients, we have a scalar autoregressive process of order p. So here ALMZ represents the spherical coefficients of the noise Z, and these parameters, phi1, phi are respectively the eigenvalues associated to the operators phi1, phi p. And this is just a stationarity assumption and unidentifiability assumption. Estimation, as I told you, we are going to estimate the kernels k. Here, I'm focusing on the simplest case of p equal to 1 for simplicity, but all the results are extended to the general case. So here we have k and our kernel, and we are going to estimate it in a non-parametric way, let's say. So based on this spectral representation in terms of this deterministic function that are called the Legendre polynomials and are associated to the spherical harmonics through this addition formula. And here we see the phi, so the eigenvalues associated to the spherical operator phi with respect to the eigenfunction, which are essentially the spherical harmonics. And observe that the inner product here is essentially the cosine of the angle between the 2 points x and y. So it's an element on the interval -1, 1. So for our results, we are going to reparameterize k to be on -1, 1. And this is a smoothness condition. So
Alessia, sorry if I interrupt you. It seems that your screen is frozen. Could you try to stop and share again?
Yeah, that was my problem today, this morning. So sorry, now you can see it.
We are waiting. It says that I started screen sharing, but it is stuck. This, try again, please.
So I'm sorry, I'm very sorry. I don't know why it's doing this in this way. Okay. Now?
Let's wait for some seconds because it says that it has started screen sharing, but it's still black.
I'm very sorry. I don't know why.
Don't worry, Alessia. It's not a great deal. Take your time to try to.
Nothing?
Not yet. We can try again, of course.
Okay, let's do like this.
Okay, now we see the screen. Okay, try to go to move between the slides just to see if yes, it works.
Okay, so I don't know if okay. So I was here, I think. And this is, I was saying that this is a smoothness condition on concerning the decay of the parameter phi L as L to the minus beta, and beta is a smoothness parameter. Here, beta greater than 1 entails that the operator phi is a Hilbert-Schmidt operator, and this is a stronger condition with beta greater than 2, which implies phi to be a trace class operator. So here our estimator that we propose in Caponera and Marinucci 2021. K-hat is a functional estimator, and it is the result of this minimization problem, which is essentially a sum of square residuals, where the square is a squared norm. Since we are treating more complex objects, we are going to assume that we can observe the whole sphere at time t, from t equal from 1 to n. And we are going to minimize this minimization. We are going to minimize the objective function with respect to this space. So using, as I told you, the spectral representation of K truncated at frequency Ln. Ln will be a sequence that goes to infinity as the number of observation in time goes to infinity, n. And so this means that if we increase the number of observation in time, we are going to we can observe the field at higher and higher resolutions. And these are the main results for these estimators of consistency in L2 and L infinity norm, a quantitative central limit theorem for the finite dimensional distribution. I will show you what I mean for quantitative later. And under a stronger assumption, a weak convergence result, so convergence of the finite dimensional distribution plus a tightness result. This is the consistency result, so we are assuming that Ln goes to infinity as n to the power d. And these are the L2 consistency and the L infinity consistency, so the subnorm. And here, as usually, we have two components, one representing the variance and one representing a bias. So we have, as usual, a bias-variance trade-off. And here we see beta, so the smoothness parameter. So we can say that the smoother is the function, the easier is the estimation in terms of rates. And this is a simulation study that showed the mean square error, so the L2 error, and the green line is our upper bound. Here, the quantitative central limit theorem for the finite dimensional distributions. So for any collection of Z1, Zm in -1, 1, we can compute our estimator, subtract the mean, the true value, and rescale for a proper quantity. So here we have the finite dimensional distribution, and we prove that not only this quantity converges to a standard Gaussian distribution, but also we prove the rate of convergence in Wasserstein distance. And this is why we call this quantitative central limit theorem in this sense, because we give this rate in terms of a distance between distributions. This again a simulated example. This blue line is our upper bound, and these are Wasserstein distance computed at different points. The last final result is under a stronger assumption, so assuming that K has a finite expansion in the Legendre basis, so up to this fixed integer L. And here we can see a functional central limit theorem, so a weak convergence to a Gaussian process with a proper covariance. So let's move to the application, which is an ongoing work with Federica Spoto and Pierpaolo Brutti. So we focus on this temperature anomalies dataset. So essentially, we took temperatures all over the Earth from 1948 to 2020, and we subtracted a long-term mean. So temperature minus a long-term mean in this annual scale. These are called anomalies. And here we model these anomalies using this change point model. So we introduce some extension to our previous model, introducing a change point, so a form of non-stationarity or local stationarity, and also anisotropies in the mean, introducing this to function mu1 and mu2, which belongs to L2 S2.
Alessia, sorry, 3 minutes left.
Okay. Then we compute the best change point, which is 9082, according to an, let's say, functional Akaike information criterion. And these are some results we plotted here. The estimated mean surfaces before 9082, after 9082, and their differences. And here in the second line, we have positive and negative values. So the blue corresponds to negative values, the green corresponds to positive values. And we can see an overall, since the anomalies represent an increase, since a positive anomalies represent an increase with respect to the base period, and negative anomalies corresponds to a decrease with respect to the base period, we can see here is evident that we have an overall increasing in the temperature, especially at the south and north poles. And this is, as I said, an ongoing work. So we are, our goal now will be to, using, for instance, the previous results I have shown you, to make some inferences on the parameters of this model. And what I can say is that usually in this context, people that work on temperature anomalies maybe do not account for the spatial component, or just or do not account for a spatial dependence. So here we are incorporating both spatial and the temporal components, and here, so this work can show not also global behavior, but not only a global behavior, but also a local behavior. So these are some my main contribution on these topics, and thank you all for your attention.
Thank you very much, Alessia, for your nice presentation, a virtual club. Unfortunately, we cannot meet in person, but this nice thing of having webinars online allows people from all over the world to follow this. First, before asking possible quick questions, I just remind everyone that you should have been warned when entering the meeting that here the webinar is recorded. I would see if there are some raised hands. I would just leave the time for maybe one or a couple of quick questions, so that we don't leave too much time to the others, and of course to the discussant. Please, Andre.
Thanks. Maybe just one short question, possibly also to stimulate others. But you were using change point analysis. Would it be possible to construct it also in an endogenous manner? How do you choose the very change point that you use? Thanks.
Sorry, an endogenous?
So how do you select the change point in your analysis,
okay.
in the application?
Okay, so basically I have some slides here. Basically, here we have the general model, and this reflects, as I told you before, also on the ALM coefficients. So we have this kind of model for the ALM coefficients, and we assume to observe a finite set of ALM coefficients, since we are able to observe all over all the sphere. And we use a log likelihood approximation, which is standard for AR models, which is this one. And then we select tau, which minimize this log likelihood. So here, since this is constant, here we have just this part, and we are going to select tau that minimize this this part, so up to the frequency L. And yeah, this is
okay. Okay, I see several hands raised. Please, Sebastian, you can unmute yourself. We can't hear you, so okay, now yes.
Thank you for the nice talk. I think the results were very strong, but I have a couple of questions regarding the the theoretical results were constrained on spheres, but I also work on this kind of field, and I'm not sure what is the positive effect to just take a look on spheres instead of general separable Hilbert spaces. Do you have other conditions which just are useful in that kind of setting, or would you say you did it because you know where you are going with the applications?
Okay, there is a reason for our result to be presented, especially on the sphere, because since we are assuming not only stationary but also isotropy, here we have these results which hold for any x on the sphere. So for any point x is an L2 omega result first. And we also, since our assumption, because of our assumption, we have that the spherical harmonics represents the eigenfunction of both the operator phi and the covariance function of the field. So this is also an important point. So there are some parts that are related, strongly related to spheres.
Okay. I would have two other questions, but I think it would be better if you let the others ask the questions.
Oh, yes. Thank you, Sebastian. I think that perhaps you could write additional questions in the chat. So if we have time afterwards, after the discussion of Dr. Park, of course you can ask additional questions. Now,
thank you.
Thank you, Sebastian. I'm sorry I'm not able to satisfy everyone. We must go forward. I saw also a hand raised by Zhang Mimi, but please let's move the rest of the discussion about presentation of Alessia after the discussion of Park. So the next speaker now, thank you, Alessia, of course. The next speaker is Alexander Volkmann from Humboldt-University of Berlin. So he's going to present his work, Multivariate Functional Additive Mixed Models. So Alexander, the floor is yours. Thank you.
Yes, thank you very much. And first of all, thank you for giving the opportunity to talk about our project here. So I'm going to present our project of multivariate functional additive mixed models, which will be a little bit less technical than the previous talk. And this is joint work together with Almond Stöcker, Fabian Scheipel, and Sonja Greven from Berlin and Munich. So first, I would want to give a motivation into what we mean when we're talking about these multivariate functions. And then I will try to give a short overview of the building blocks that we're using to construct our multivariate functional regression model. And then I will give a short, I will show some small results from the applications that we have. Okay, so first of all, when we're talking about multivariate functional data, we think of functions that are observed on the same domain, but at the same time point, we actually measure several functions. And this can actually happen pretty often in reality. So for example, if you're thinking of the general concept of weather, then you can measure the temperature at a specific point in space, as well as the precipitation. And then you have two univariate functions that actually can be interpreted also univariately. But then there's also these this different type of multivariate functional data that is, well, maybe a little bit more inherently multivariate in that you're not really able to interpret the univariate dimensions. And one example would be, for example, movement trajectories, because there you follow a point of interest over time in a coordinate system, and then the axes don't necessarily have to give you a good univariate interpretation. And for these types of data, multivariate analysis would be more of like a natural approach to do that. And in our project, we have examples from both these types of multivariate functional data, but here I would like to present the example that we have with movement trajectories for snooker players, because we have data from a snooker study where 25 players participated, and they wanted to study the effect of a training program for the snooker players. So they wanted to see whether they could change the muscular coordination of the snooker players, and if this training program would then affect the mean trajectories of a snooker shot. And so the 25 players that were they were divided into treatment and control group, and they were recorded on video in 2 sessions before and after the treatment or the training period. And then we get this nice nested study design with overall 296 multivariate functional observations. And when we're now talking about multivariate functional observations, we actually record 3 points of interest. You can see this in the slide before. So we're interested in the movement trajectory of the hand, the shoulder, and the elbow. And you can see that these blue lines, they represent the movements throughout the time of the snooker shot. So we basically end up with 6-dimensional multivariate functional data where we record the X and Y positions over the time of the snooker shot. And then we also want to include further covariates of interest, for example, the skill level. So here you can see a plot of the data that we're working with. Here, these are the hand trajectories for unskilled players. Here above, you can see the elbow movements, and these are the shoulder trajectories. And now we basically want to develop a multivariate functional regression model where we can include flexible covariate effects. And we also have to account for the design of the study. And we want to do this by including functional random effects. And in order to develop our model, we will then actually build on existing models for univariate functional data and combine these. And so now I'm going to talk a little bit about the building blocks. The probably most important building blocks is a very flexible framework for functional regression, for functional responses. It is called Functional Additive Mixed Model, was also proposed by Fabio and Scheibel et al. And this framework allows to include linear and nonlinear effects of scalar or functional covariates and also interactions of those. And you can include functional random effects, which are also very important in a way, because the idea behind these functional additive mixed models is that you reduce the functional regression task to a scalar additive mixed model. And then you can account for the correlation of the observed data points that you use for the scalar additive mixed model by including functional random effects for these observations within one function. And then the estimation of your regression model is basically analogously to scalar additive mixed models. So you can fall back on this entire toolkit that has been developed for additive mixed models. And you're using all of the different penalized maximum likelihood methods, for example. The second building block is then helpful for including or incorporating our nested or cross study design, because here we rely on a paper by Zederbaum et al., where they decompose the overall covariance function of the observed functions into contributions by different functional random intercepts. And then for these different functional random intercepts, you estimate the covariance operator, and then you can decompose this using a functional principal component analysis. And then you basically include these parsimonious basis representation in your functional regression model and can therefore represent your functional random effects. And the third important building block is now where the multivariate nature comes into play. This is with the multivariate functional principal component analysis, which was, or this specific paper by Happ and Greven is very useful here because they show that you can estimate the multivariate functional principal components based on a relationship with univariate functional principal components. And so you can basically get a very parsimonious representation for your functional random effects, and you explicitly capture the dependency between the dimensions, but you don't have to explicitly estimate the covariances across the dimensions. So that is a very nice tool to have here. And now with these three building blocks, we can actually construct our multivariate functional regression model. And like I said before, the FUM framework basically works with the evaluation points of a function. So we are assuming that we have this multivariate functional response yi star, but we're only working with the noisy evaluations. And then we can include here partial additive effects of fixed effects or other functional random intercepts. And just to make it very explicit, we have this multivariate smooth residual term, which is a, so to say, a functional random intercept for the functions. So you can account for the correlations within the functions. And we also include a scalar or like multivariate white noise error term, a residual term, to account for the residual effects of the noise evaluations. And the way that we want to represent or include our functional random intercepts in the model is by using truncated multivariate Cahoon and Loewe expansions. So basically, we are assuming that all of the functional random effects are independent copies of a stochastic process. And then we use this representation with the multivariate orthonormal eigenfunctions psi and the uncorrelated scalar scores rho. And this gives us then a very parsimonious representation for the functional random effects. And we can do this for all of the functional random intercepts that we want to include in our model. Then we basically take the all of the observations that we have, all of the evaluation points, and we construct a scalar additive mixed model for those where we have fixed effects matrices, and we want to estimate a coefficient vector that will then give us the smooth covariate effects. And we include a model matrix for the evaluations of the eigenfunction basis. And the nice thing here is that you can see we present this for now as a dimension-specific model formulation. So you can include different fixed effects for the different dimensions. But the nice thing is that this vector of rho, this set of normal scores, is basically gives us the entire dependency across dimensions. So this is independent. Sorry, this is independent of the dimension D. And now we can combine all of these univariate representations into our big multivariate functional regression model simply by stacking the dimensions on top of each other, and then relying on like this different matrix representations to get a diagonal block structure for the fixed effects, for example. But given that the rows are independent of the dimensions, we can simply stack, for example, the matrix the model matrices for the eigenfunction evaluations. And the way this model is now estimated is basically taking all of these three building blocks that I talked about before together, because first of all, we look at the univariate dimensions, and we use the building block number 2, where we were able to separate the different functional random effects for each dimension separately, and we estimate univariate functional principal components. And then we use the building block number 3, where we use the univariate functional principal components to estimate the multivariate functional principal components. And those we will assume as fixed, so to say, and plug them in as an approximate basis, a very parsimonious basis, in this big FUM model that we have seen before. And then you can basically fall back on all of the implementations that you have for scalar additive mixed models, which is a very broad class of models. And of course, this estimation process is also made available for everyone out there in a R package, which you can access on GitHub. Now I will jump to the application, and just as a reminder, these are the data that we're talking about. So we have these snooker trajectories, and in order to model them, we include the skill of the snooker players, but we also include the treatment or control group of the person, as well as if the snooker shot was observed before or after the training period. And then this interaction term would give us the treatment effect of the training. And this is then primarily what the researchers are interested in. And to account for this nested study design, we actually include 3 different random intercepts. We have one functional random intercept for the person, one nested random intercept for person and session, and then we have this functional random effect, the smooth residual, for the correlation within the functions. And maybe one important part, again, is to note that all of these functional random intercepts are represented using truncated Cahoon and Loewe expansions. And so we have to find a way of choosing the truncation order. And here in this application, we want to, or we let the model pick as many functional principal components that are needed to explain 95% of the variance that can be found over all of the different dimensions. So basically, the model itself chooses how many functional principal components to use as basis functions for all of the functional random intercepts. For example, for the player-specific functional effect, we get 6 multivariate functional principal components. And the nice thing with the spaces is now that you can also interpret these functional principal components. For example, here in this plot, you can see the estimated mean in black, and then we add or subtract 2 times the first principal component of the player-specific functional random effect. And this effect overall accounts for about 15% of total variation in the data. And the nice thing with this effect was then that the researchers had argued from a theoretical perspective that there's actually 2 ways of playing snooker. One, you can fix your elbow, and then your hand does more of a pendulum motion, whereas you can also dynamically move your elbow, which would then result in a more flat hand stroke. And we kind of like to interpret this functional principal component in that way, where the blue line shows that the elbow is a little bit more fixed, so we get a little bit more of a pendulum motion, whereas if you dynamically move your elbow, the red hand movement is contracted a little bit and resembles more of a straight line.
Sorry, Alexia, I have just a couple of minutes left, please.
Yes. This is, of course, the interpretation for the basis functions that we're using. But of course, we're also mainly interested in the estimated covariate effects. And just as a quick result, we didn't find any really notable effects for the treatment effect. So it doesn't appear that the training did anything to improve or to change the movement trajectories. But this one is the skill level, and you get some inference also readily from the scalar additive mixed models. If you're looking, for example, at the univariate functions that are estimated, because then you can look at the pointwise intervals, and you can see, for example, that for the hand trajectory, you find that there are areas that seem to be different. Okay, so overall, we basically developed a multivariate functional additive mixed model where you can include flexible additive effects of scalar and functional covariates, but also functional random effects to incorporate or to account for different study designs. And then the models are, in a way, very parsimonious, because you get this, the dependency between the dimensions with simple scalar scores. And in our simulations, we could also see that the mean estimation is also quite robust, especially if you're looking, for example, at sparse data scenarios. And yeah, just overall, we think that is a very nice way of looking at data that are comparable to these movement trajectories. Yeah, that's it. These are my the references. Basically, those are more or less the building blocks that we're using, and thank you for your attention.
Okay, thank you, Alexander, for your nice talk. Okay, let's see if someone, okay, I see some claps, so virtual claps also from my side. Let's see if someone wants to raise his hand. Of course, we have one question from Sebastian, so you can turn on your microphone, Sebastian.
Sorry, it was a mistake. I wanted to make
it. Okay, that's nice. Do we have someone else wanted to a question? No? Andre?
Thanks. It was a great talk again. Maybe just one short question. For the regression that you use for the model, are there any specifications? I mean, could there be correlations between the different parts of the model? Are there any specific assumptions that you make? In the paper, you mentioned the distributional ones and so on. Thanks.
Yes, well, we are assuming that all of our functional random intercepts are uncorrelated or independent, actually. I think that is very important for the model identifiability. And then for now, we're also assuming that the fixed effects are basically independent over the dimensions, but you could definitely change that and extend our model in that respect, I think.
Okay, thanks.
Okay, I just have a small curiosity, just if there isn't anyone else raising its hand. Okay, so I just, quick question. Sorry, only if I understood well, actually. The functional random effects that you propose, do they only involve the random intercepts? Is it possible to set also random slopes? Do you think this is possible? Maybe it's computationally too intensive. I don't know.
Yes, we have kind of started thinking about this direction. I think it should be possible to implement this, but the computational intensity is definitely an aspect that that one should address. But the way that the model works, or like the way that the separation of the covariance happens, could also work for random slopes, I think.
Okay, so the problem is mainly computational, as I expected. Perfect. Thank you again, Alexander. So I would now move to the next speaker. Here, I would say, welcome to Fabio Centofanti from University of Naples, Federico II from Italy. he is going to present his work entitled Sparse and Smooth Functional Data Clustering. Okay, you are going to share your screen. Now it has appeared.
Can you see it?
The floor is yours, Fabio.
Okay, thank you. Thank you, Christian. Good afternoon, everyone. I'm Fabio Centofanti from the University of Naples, Federico II, Department of Industrial Engineering. And the title of this presentation is Sparse and Smooth Functional Data Clustering. This is a joint work with Antonio Lepore and Biagio Palumbo from the University of Naples. This is the agenda. After a brief introduction, the proposed method for functional clustering will be presented. Then its performance will be assessed through a simulation study and 2 real data examples. At the end, some conclusion will be discussed. In the last year, due to advances in technology and computational power, most of the data collected can be modeled as functional data. Cluster analysis is an important topic in functional data analysis, whose aim is to classify a sample of curves into homogeneous groups without any prior knowledge. This is an unsupervised task. In multivariate cluster analysis, some attributes variables could be completely non-informative to identify cluster. This is the example in the case of high-dimensional problems with a lot of variables. Therefore, the task of identifying the variables which respect the true cluster differ the most could be of great interest, both because of a more accurate identification of the groups and an higher interpretability of the clustering result. Methods that are able to identify informative features are referred to as sparse methods. Sparse clustering has received increasing attention in the recent literature, but in functional data analysis, the notion of sparseness has appeared only recently by Floriel and Vitelli 2017. The aim of sparse method for functional data clustering is to cluster the curves while jointly detecting the most informative portion of the domain. Now we talk about portion instead of variables. In this regard, we propose a model-based procedure to sparse clustering of functional data. This is named Sparse and Smooth Functional Clustering, SASFUN cluster, where the parameters of a general functional Gaussian mixture model are estimated by maximize a penalized log likelihood. In this penalized log likelihood, the key element is the functional adaptive pairwise future penalty. The SASFUN class method is based on the general functional clustering model introduced by James and Sugar 2003, where we assume that there are n functional observations spread among G unknown clusters, and the probability to belong to a cluster is Pg. Moreover, conditionally on the cluster membership, the vector of response Y is modeled as this expression, where Gi here contain the values of the function Gi, which is assumed to be a Gaussian random process with mean mu G and covariance omega G. Moreover, the non-component label vector Zi is assumed to have a multinomial distribution. This vector is a vector of 0 and 1, where the id entries, the G entries is 1 when the id observation belongs to the G cluster. The last assumption is referred to the functional form of the problem. We assume that each function Gi may be represented as a linear combination of basis function here. With this assumption, the log likelihood function corresponding to the observed vectors can be expressed in this way, where the unknown parameters are the probability to belong to a cluster, the coefficients corresponding to the cluster means, the variance covariance matrix corresponding to the coefficients of the observation, and a parameter which is related to measurement error. Instead of maximize the log likelihood, we propose to maximize a penalized log likelihood, where the penalty function has this form. With the assumption of, we assume that each function can be estimated, can be approximated through a linear combination of basic function. With this assumption, this is the final form of the penalty, where the first element here is the functional adapting pairwise penalty, whose aim is to shrink the differences between every pair of cluster means for each value of t. For example, this summation means consider every pair of clusters. Here we have the difference between the mean of cluster G and the mean of cluster G prime. This function theta G prime make this penalization similar to adaptive lasso, because what we want is that the penalization is larger where the cluster means are very similar. On the contrary, the penalization should be small where the cluster means are very separated. The last term is a smoothness penalty, whose aim is to further improve interpretability, because with this penalty we constrain the resulting means to be smooth, cluster means to be smooth. Okay, to estimate this model, we make the most important assumption. We assume that the mean differences for each G and G prime is approximated by a piecewise constant function. This assumption is valid for basis functions that are, for example, B-spline, for B-spline basis function, and the approximation error of this approximation decreases as the dimension of the basis set increases. With this assumption, we have an optimization problem, which is a function of the absolute value of the coefficient corresponding to the cluster means. To solve this problem, we design an expectational conditional maximization algorithm, which is a modification of the expectation maximization algorithm proposed by James Juhyun. The conditional step is needed when we have to maximize with respect to the coefficients of the cluster means, because this maximization with respect to this variable has not a closed form solution because of the presence of the absolute value. Therefore, we consider a local quadratic approximation of the absolute value, and therefore we consider an inner loop to solve this optimization. Then, to define a solution, the optimization problem, we have to choose some hyperparameters. Specifically, we consider B-splines, cubic B-splines with equally spaced knot sequence, whose dimension should be as large as possible in order to reduce the approximation error in the pairwise penalty. And then the choice of G, lambda S, and lambda L, that are the parameters corresponding to the penalties, and G is the number of clusters. We propose to choose these parameters by means of a k-fold cross-validation procedure. So now we have all the ingredients to define the solution of the SAS-Font class method. Okay, let's talk about a simulation study. We compare the proposed method with the several competing methods. We consider filtering approach based on smoothing B-splines, filtering approach based on functional principal component. We consider the distance-based method proposed by Yev et al. 2013, and we consider two model-based procedures, curve class and fan HDDC. As performance metrics, we consider the just rand index, which measures the agreement between the true data partition and the clustering results. We measure this measure when the true number of cluster is known. To assess the performance in selecting the true number of a cluster, we consider the mean number of selected cluster. Finally, to assess the estimation performance of the cluster means, we consider average root mean square error of the cluster means. These are the scenarios. We consider three scenarios with increasing number of clusters and decreasing portion over overall non-informative portion domain. In this plot, we see the result of an example for the proposed method. We see that the proposed method is able to identify the non-informative portion of domain, that in this case is from 0.2 to 1, because the corresponding cluster means are fused on this domain, whereas it's able to identify the informative portion of domain from 0 to 0.2, where the cluster means are separated. The same for the other scenarios. Note that we consider informative portion domain for each cluster pairs, because, for example, in this case, this portion of domain from 0 to 0.1 is non-informative for these two clusters, but is informative for this cluster and this cluster. Okay, in terms of A-rand index, we see that the proposed method is the best for several values of measurement error. On the x-axis, we have a measurement error. In all the scenario considered, we see that the best competitor tend to be curve class, which is a model-based procedure based on wavelet decomposition. In terms of mean number of clusters selected, again, the proposed method is the best one in all the scenarios, and also in terms of estimation error of the cluster means. But I think this is the most important results. In this table, we see the correctly identified fraction of non-informative portion of the domain. The larger this value, the better the performance in terms of interpretability. Of course, we consider only the proposed method because it's the only one which is able to identify non-informative portions of the domain. As you can see, the values are very large and very similar, very near to 1, which is of course the maximum in this case. This demonstrates the performance of the proposed method, which provides results that are of course more interpretable with respect to the competitors. Okay, let's talk briefly about two real data examples. The first example considers the Berkeley growth stated dataset, which is a well-known dataset in the functional data analysis literature, where we have curves corresponding to growth velocity for 54 girls and 39 boys from age 2 to age 17. These are the curves. The aim is to cluster these curves. We see the result only for the proposed method, and here it's clear the feature of the proposed method, because we see from 2 to 10 that the two clusters identified have the same mean. Whereas from 10 to 17, the clusters means are separated. So we interpret in this case that difference in the growth velocities appear from an age from 10 to 17 and not from 0 to 10, which is in this case the non-informative portion of the domain. These are the results, the clusterized curves. The second example, then we are done, is an example which studied the EcoSAF project dataset, which contained 538 dynamic resistance curves collected during resistance spot welding lab tests at Centro Ricerche Fiat in 2019. These data are available online on GitHub at this link. These are the functions. We focus on the first derivative again, and these are the results. We have the proposed method identifies 3 clusters, and the important thing is that these clusters are separated in the first portion of domain, which is for this reason informative, whereas are fused for the remaining part of the domain, which is non-informative. In particular, we see that cluster 1, the black one, and cluster 3, the green one, are fused for 0.4 to 1. Whereas cluster 2 is only fused from 0.8 to 1. These results can be used in further analysis, for example, to set up a monitoring strategy with respect to these curves. Okay, to conclude, I presented the SAS-FUN class method to cluster functional data, which is a sparse method whose key element is the functional adaptive pairwise feature penalty that allows pairs of cluster means to be exactly equal over non-informative portion domain. This helps both the interpretability of the results and the accuracy of the result, as we saw in the simulation study. We consider also a smoothness penalties because we want to smooth cluster means. This further improved interpretability. Then we assess the performance of the proposed method through an extensive Monte Carlo simulation study, and we apply the proposed method to a real data to real data examples. To conclude, the proposed method is implemented in the R package as fun class, which is available on CRAN, and the developed version is available on GitHub. Okay, that's all. These are some references. The most important one, of course, is the third one, which is the paper on which is based this presentation, Sparse smooth functional data clusters. Thank you for the attention.
Okay, thank you very much, Fabio. You also for being perfectly on time. And I see many hands raised. Oh, 6, 7, so many questions. I'm sorry, I'm not able to see who was the first one. So, okay, there are fewer hands raised. Okay, who wants to speak first? I would go with maybe Alessia. Did you have the hands raised?
No, it was just a virtual club, not a raise hand.
Ah, okay, so it is my confusion. I confused the hands raised with virtual clubs. That's the reason so many. Virtual clubs, of course, also from me, Fabio. And let's see if anyone wants to, yes, there are virtual clubs. If anyone wants to ask some questions. There's Andre. Please, Andre.
Thanks. Just one small question. You mentioned that your model, I think, is based on Gaussian random process, right? In there. Would it be possible also to construct this in a different manner, on different model-based assumption? Thanks.
Yes, of course, it can be constructed with different distribution. I think, for example, at the T distribution, which could make this model robust against, is a method to make this model robust against outliers. But I think the Gaussian distribution is the most general distribution in this case, and of course is the most used. But of course, this method can be further extended to include different kind of distribution.
Sorry, is there any computational advantages for applying Gaussian random process?
Of course, the solution in terms of this make, of course, the computation very, very easy for the expectation maximization algorithm, and it's very standard. Of course, when you use more complicated distribution, the computation can become more difficult, and maybe this is the case. And so, yes, I think that the Gaussian distribution is the simplest one in terms of computation, because for example, in the expectation maximization algorithm, in the maximization step, all the maximization with respect to parameters have closed form solution, except, of course, as I said, with the maximization with respect to the coefficient corresponding to the means. But this is, of course, depends on the assumption of Gaussian distribution. So the assumption of Gaussian distribution is crucial for the computation, for a computational point of view.
Okay. So I don't see any other hands raised. So I would say thank you again, Fabio, for your presentation. And now it's time for the discussion. So I want to say welcome to Dr. Juhyun Park. So okay, perfect. You already started sharing your screen. Dr. Juhyun Park holds a PhD in statistics, which has got at the University of North Carolina. And she was lecturer in statistics, and she worked at the Lancaster University in the UK. And currently she works at, sorry for my bad pronunciation, I don't speak French. It should be École nationale supérieure d'informatique pour l'industrie et l'entreprise, if I'm correct, pretty long name. And her research interests, and one of we asked her to be as this discussant because she's very active in functional data analysis. She works also on statistical modeling and inference and non-parametric inference. But of course, she's active, as I said, in functional data analysis, and also its applications. She works on semi and non-parametric approaches, and she also focuses on multivariate functional data, as we also saw today in the work of Alexander, for example, clustering methods. So we think she's the ideal discussant for today. So thank you for accepting our invitation. And now, please, Dr. Park, the floor is yours.
Okay, thank you. I didn't realize that the discussant is also as important as speaker. It was thanks for all the speakers. In fact, it was a very hard work. There were so many interesting and stimulating ideas to perhaps not only just to discuss, to point out, but I try to keep it short. It's not my job to bring all this one. It's more my sort of a reflection on what I have learned and seen. So this as I guess our subject as the subject says, the all three talks nicely present, also demonstrate the important advances in functional data. So my very first question is, what is a functional data? Perhaps everybody knows, and where are we going? So as in traditional sense, that we consider functional data as one-dimensional curves, the L2, but it has already gone through the one-dimensional curves. Doesn't have to be just these functions as we define it. Functions also can be viewed in a complex domain as S2 or sphere, but also we can imagine that it can be a function of a very complex domains as we can go further. And also the univariate now already moved on to the multivariate. Perhaps sooner or later it will be high dimensional. It's already happening. So all these still our talks today are nevertheless it's L2 spaces with a relatively a nice structure that we can talk about the variability through the essentially the variance and not too far away from the Euclidean spaces that we used to work with. In terms of context now also, perhaps the talk course can be discussed in slightly different ways. The last talk, the clustering, of course, the clustering is or can be viewed as a missing covariate, that we don't have a covariate. Whereas if you think about this spherical function, a random field, that it's how do we, in the context of a dependence structure, that how do we deal with the dependence of not just ordinary dependence point-wise, but as the global functions. And the Alexandre, the Volkmann, they in fact included many covariates that, okay, so many, it can be as many as, it's still the question, but in functional data analysis also, now is possible to have a very complex statistical modeling that we could also present. In terms of a structure, the structure, I said the structure, that is something extra, the structure information that perhaps a functional data can bring or utilize more efficiently. So the clustering, I guess in the context, it was the information about more like a domain selection, that how do we look at the domain selection problems in the clustering context where we don't have a clear the grouping. The structure information in the spherical random field is also, again, the sphere is a special, has a manifold structure that allows for a certain efficient representation that is also well exploited. The multivariate, multivariate functional additive models. Now the random effects is a way to extend our variability in functions in many in more complex or more I guess informative way. The focus, I said, the algorithm theory modeling, of course, is one doesn't go only for theory, only for modeling, only for algorithms, but these are just the important aspect that just to show the breadth and the depth of the advances in the field. Of course, this is not the end of the list. I only added one line, but we could imagine, or already is happening, that functions can be in line with the object-oriented data analysis. People are working with the more random objects with the more complex structures, not necessarily with this Hilbert space, and the context is getting ever more complicated. And I guess interpretability is still the rising word, is both in statistics and machine learning, high dimensional. We don't really agree on what interpretability really is, but nevertheless becomes important concept in the data analysis in general. And I think it's will become, I guess, even more important. How do we formulate in the context and functional data? Of course, it's a different question, an important question. What is a functional data approach? That, of course, we cannot define it as a simple way as possible, but just looking at in glance, more or less, we have some ideas of parsimonious representation of functional model that brings the infinite dimensional problem into some finite dimensional problems. And then we tend to apply some the machineries from a non-functional techniques. I think it is a practical, and also we tend to still stay in the very much Gaussian-like model. It's a bit too simplification, but nevertheless, for these talks, perhaps we have a more like Hilbert space, a more general structure, but certainly more general types of data that we will see even more the general new ideas coming out of or going over these ideas further. Just a small point for each talk, if I just make it. For the clustering, I think essentially somehow try to combine the interpretability and domain selection and somewhere between. And sparsity. So these concepts are not as clear as for functional data. That it's and even and also the lasso type of the penalty is really pointwise sparsity. That is developed, whereas our sparsity as a domain selection is like a function. I think they formulated somewhat functional way, but mixed two different sort of conceptually. There was some natural transition, which was not so obvious. And also this adaptive penalty, that was, I think, okay if we can define least squares method as an estimator to begin with. But other than that, I think it is thinking of adaptive penalty, I find it a bit difficult to justify in more general sense. Practically, yes. And also for functional data, I guess if we look at this inverse, the differences of continuous functions, then I suspect that these zeros or close to zeros for functions is not occurring just point-wise. It's more like in the interval that perhaps needs some further consideration for this type of the penalty that can be realized in the functional data. The spherical functional data with a functional time series. So they developed this extension, beautiful extension for the spherical random field. It importantly start with this nice representation, harmonic representation. So that is the basis of the development. So I try to understand or try to make a link that we used to work with the functional PCA of a representation, which has just a standard representation of independent. Whereas now if we look at the functional time series of a spectral analysis, we have this two level of representation through the spectral, the Fourier density, spectral density. And again, under this spectral density with the different frequencies, we have this double layer of these expansions that was developed for just standard Euclidean data, not for the manifold data. But the difference here, I think here is that in the standard case, we don't have this luxury of we know there exists a representation, but we don't really have this clear knowledge about the eigenfunctions or the autonomous basis itself. Whereas it seems to me maybe that the sphere has a lot more structural information that could be utilized, and especially if we even assume the isotropy, that further simplification was possible. Of course, the natural question is this a benefit or this structural information can go further? Non-isotropy is not only just extra means. If we think of really sphere, I would think that the rotation really also location does change the dependence, that perhaps the extension might come later on the way. The multivariate functional data, of course, it's now there's no excuse for not fitting the proper functional regression models. That they put together both this complex mean part and also complex variance part. In a standard framework, the linear mixer effect models that people would like to have. Of course, it's great to see that we are pushing further, but also at the same time how far we can go. So this variance decomposition, people already have mentioned that is only the intercept or the other covariant dependence, but also exactly is there somewhere we have some ways of formulating or this having ideas of how to decompose also the variance in multiple I guess the crossing in crossing cases. And also, it is good to utilize this computational methods. But again, as already has been mentioned, it's not the end, it's a beginning. That is still a computationally intensive methods that perhaps there might be some further development. So that's all I want to say. That was thanks for the great the talk and also the work to all the authors.
Okay. That's perfect. So thank you very much for your discussion, virtual club, also for you, Dr. Park. And so I really appreciate this, but of course I want to leave the floor to the speakers. Okay, I'm sorry I didn't give you the order of the speaker, so you used a little bit different order. So I would say let us remain with the speaker orders. I will see if Alessia wants to say something.
Okay.
Okay, thanks, Alessia.
Thanks, Juhyun, for this nice overview of all the three talks. Of course, isotropy or non-isotropy is a very good point. As you also said, when we have isotropy, the eigenfunctions of the covariance operator are the spherical harmonics. When this assumption doesn't hold, the spherical harmonics are no more the eigenfunctions of the covariance operator. And of course, introducing anisotropies in the mean is simpler, but introducing anisotropy in the covariance, of course, is a trickier part. And so we can move in different directions. So for instance, since the eigenfunction of the covariance function are no more the spherical harmonics, one possibility could be to estimate directly from the data the eigenfunctions. This could be one possibility. Another possibility could be to introduce some form of local isotropy. So as we did for the, of course, in a different manner because it's more bit particular the case, but some form of local isotropy. Or another, so maybe these two approaches can be done in a dense regime. So the regime we discussed before. So assuming to be able to observe the whole sphere, but we can go also in another direction. So for instance, in the sparse regime. So when we assume to observe just some points on the spheres, just some sparse point on the sphere. And this is a work I'm doing here at EPFL with Victor Panaretos. So here the assumptions are stationarity in time, but anisotropy, so non-isotropy in space, and also non-Gaussianity. And we are directly estimating the covariance functions using a smoothing spline approach on the sphere. So these are our ongoing works. Thank you.
Thanks.
Okay, perfect. Thanks, Alessia. Now, Alex, do you want to add something?
Yes, so first of all, thank you very much for that discussion. I really liked how you brought all of the talks together and pointed out like the different fields that we're all like focusing on in. That was really insightful, I thought. And I think I have to agree with you to some part, of course, because we do see that the methods that we are currently developing, they are very computationally intensive. The one thing that is kind of a big advantage for us, I would say, is that we can benefit from research that is done on the level of scalar mixed models, because then we can translate this also to functional data. But of course, like you mentioned, once the data becomes more complex and we're talking even about objective data, then one really has to think of more efficient ways of computing it. And of course, like the project that I presented is only a starting point because, like you said, the more complex the variance structure becomes, the more you actually have to think about what you can do to identify different components of the variance, so to say. For example, for now, we still have to think about like some pre-processing for the data to get to account for variance in the speed of the function or so. But you could, of course, then start thinking about how to to incorporate this also in the model. But yeah, I think that's what I would like to say. So thank you.
Yes, thanks.
Thank you, Alexander. Fabio.
Return. Okay, thank you for your good point about you are concerned with the weight in the penalty, the adaptive weight in the penalty, and I think that we did some research on function regression where we use the same ideas with the lasso in order to improve interpretability, and there we didn't use an adaptive weight. And what we saw, of course, is the main drawback of lasso. The main drawback is the problem is that is a bias procedure, because when we have, for example, in this case, a mean, or in this case, a difference that very large, the lasso penalize without taking into account that you don't have to penalize in that case. So we introduced this adaptive penalty for this reason. Under the theoretical point of view, is another end, because the adaptive lasso is demonstrated to be both consistency in terms of estimation, consistent in terms of estimation, but also in variable selection. That is not the case for the standard lasso. That is not variable selection consistent in some case, or if it is variable selection consistent under strong assumption. So of course, the weight in the paper of Zhu about adaptive lasso, he said that the initial weight should be a consistent square n consistent estimator. Yes, but of course, in an applicative under applicative point of view, this means that your initial estimator should be at least good estimator, because if you consider an estimator that is not good, your penalty is not good, because you go to penalize something that you should not penalize. And of course, this is I think under applicative point of view, this is the thing. You have to choose a good estimator, a good initial estimator for your weight. Otherwise, your result could be not as good as you expect. But of course, some theoretical issues should be more investigated, because under model-based clustering from functional data, there is not a lot of work about theoretical properties. Actually, there is also not so much work in the multivariate case. For example, in the case of mixture model, penalized mixture models, there is some paper, but there is not a unified approach, a unified theory for consistency in terms, in this case, both in estimation consistency and variable selection consistency, that in this case, in this application, maybe is the most important consistent results. The other issue is about if the weight is zero, when the weight is zero, no, sorry, when the weight is infinitive, because the denominator is zero. Yes, but this is something that we want, because if, of course, the initial estimator is good, and this good estimator gives a difference that is zero, so you are good, and so you have a weight that is very large, and so you are good because your solution is good. Of course, in this approach, maybe something that we can add in future is the uncertainty on the initial estimator, and take account this uncertainty to in the use of the weight, because with this method we have faith that our initial estimator is good, and maybe can be the case that it's not the case. So it is a good point that as not a unique solution. So thank you for your observation.
Thank you.
Okay, thank you to all the speakers for responding to the nice discussion. I also appreciate, as the speakers tell, the way you tried and you managed very well to put everything into a general framework. That table was really nice. So I think that we are relatively on time. So the idea was the webinar was going to last around 90 minutes. It's 10 minutes more. If you want to add something, Dr. Park, or if not, we can see if other people want to ask questions.
No, I'm happy. I think
okay.
it's yes.
Yeah. There are some unanswered questions. I would start from the questions in the chat. Of course, after them, we see if anyone has other questions. There should be just 2 or 3 of them. Let us see. Okay, there's this one from Alayane Mohammed. I don't know if it's still. Yes, he's online still. So this is to Alexander, I think. Can this model be generalized to generalized partially linear single index model functional cases?
To be honest, I'm not very familiar with that, with this type of model. I think I would say that given that our functional regression model is or can be represented as a scalar additive mixed model, once you're able to generalize the scalar additive mixed models to this single index model, then it should also work for the functional additive mixed models. However, there's probably going to be some details worth thinking about because, for example, the identifiability of some of the fixed effects have to be considered carefully when you're doing the step from scalar mixed models to functional mixed models. And then I can imagine that once you're doing another step into another direction, you would maybe think of that as well.
Okay, thank you, Alex, for your response. There's this from Andre. Okay, I read it for you, Andre, if it's okay. So in your work, you use Malya-Weinstein approach to derive the quantitative central limit theorem. Could this approach be used in functional data analysis in general? Possibly in the work you mentioned you're doing with Panaretos. As this is an open topic in probability and asymptotic statistics, this could be interesting to discuss.
Okay. I'm not using any form of Malya-Weinstein approach for the work with Victor Panaretos, since we are not assuming any Gaussianity. So since the same Malya-Weinstein approach relies on isonormal Gaussian processes, so the Gaussianity assumption is important, but it's for isonormal Gaussian processes on general Hilbert spaces. So maybe it can be extended to some problems on functional data analysis, but assuming some form of Gaussianity.
Thanks. I just want to shortly add, because I think that this is really an open topic currently, and to SEDOM is still, I think, used in statistics, largely in some probabilistic derivations. That's why I was also asking. I think this is only one of the rare applications in functional data. So, thanks.
Okay, thank you for your question.
Okay, there is another additional questions again for Alessia from Sebastian Kunert. Is your estimator for the kernel newly established, or is a famous one from another theory field you generalize or apply to your specific case?
So, since we are using specific assumptions on the sphere, isotropy, etc., I haven't seen any form of such estimators for this particular case. So when you can assume to observe the spherical coefficients. So in this sense, I haven't seen it, but it's a simple estimator. So do you remember it's a sum of square errors? So it's the idea. It's very simple.
Okay. Oh yeah, Sebastian added something. The reason was the argument and the set, which I wasn't aware of in this context.
Okay.
If you want to add something, Sebastian, you can activate your microphone. Maybe, I don't know.
Yeah, thank you for the answers in general. Thank you for the nice ideas as well. The reason why I asked this was I also work on functional time series, and I used the usual moment estimator in a general context of separable Hilbert spaces. So I wasn't sure why this one was not used, but you said that the isotropy is, I have never worked with that kind of definition or notion because I worked on general spaces. And it would be nice for me, if there would be enough time now, to understand the big impact of that isotropy.
Okay, so.
But maybe it's too big, that question. So
the main point is that, as I said, under isotropy, the spherical harmonics plays a big role. Okay, so are the covariant, so are the eigenfunction of the covariance operator, and under the assumption of isotropic kernel are also the eigenfunctions of the linear operator phi. So in this structure gives us the possibility of constructing that estimator in that way. It's of course it's a big question to answer. So.
Okay, you can try maybe to ask through an email if you want to expand the discussion. You can do this in a different setting, just because now we are a bit out of time. But if someone else wants to add something or wants to ask additional question, is welcome now before closing the event. Is there anyone else willing to ask questions? Or maybe comments? Okay. I think we are all satisfied then. That's perfect. So it's time to close this event. I want again to say thank you to the speakers, to Alessia, Alexander, and Fabio, and to Juhyun, to the discussant. You have all done nice work, nice presentations. And I remember that this video has been recorded, so you are going to see this online. And that's it. So Andre already remembered at the beginning the next webinars organized by YoungStatS. I'm happy I was pretty involved in the organization of this. If you just want to add some words before closing, Andre, since you're the coordinator, I have finished.
Thanks. Nothing big to add. Congratulations for all the thoughts and the excellent discussion, and hoping naturally you all follow the work of YoungStats and the webinars that Christian mentioned, but after the holiday break. I think we all need it, I would say, after the pandemic and everything. Thanks.
Yes, indeed, we need some breaks after this long period, hoping that it's going to get better and better. Well, I think we can say goodbye to everyone. Thank you very much again, and see you soon.
Thank you.
Bye.
Bye.
Thank you very much. Bye.
Bye-bye.